Half-life is a pretty common thing to talk about when you are talking about radioactive material. We are going to look at a few radioactive materials that are used in the United States for power. So let's take a look. The half-life of a substance is the time required for half of a given sample to disintegrate. The United States has over 70,000 metric tons of nuclear waste. Scientists and environmentalists are concerned because these hazardous materials will continue to be dangerous for thousands of years due to their long half-lives. Two common nuclear power sources and their half-lives are below. Plutonium-239 is 24,360 years. Radium-226 is a little better, 1,620 years. What we mean by half-life is not that after 2 iterations of that, it's gone. Let's look at this example. After 24,360 years, 224 grams of plutonium-239 will decay to half of that, half of the 224, which is 112. It is not true that another 24,360 years later that it's all gone. What happens is half of that, the 112, is gone after 24,000 whatever years. So what is that? 56 grams. And then another 24,000 plus years later, it'll decay to 26 grams because half of what is there is gone 24,000 years later. So you can see how this type of decay, it's not linear. Linear decay would be it went from 224 to 112 and then down to 0, all in one, in those 2 jumps, because it makes the same change in how much radioactive material is there for the same change in time. That would be linear decay or linear decreasing. That's not what happens with radioactive material. It decays exponentially because each time it is getting multiplied by half of what was previously there. Let's use the idea of the half-life of radium-226, that isotope of radium, being 1,620 years, to find an exponential decay model for radium-226. We know that when T is 1,620 years, A would be 1/2 of the amount you started with, right? That A naught is the amount you start with. We're not given that here, and we're not going to be told that here. We're not going to use that here. We are going to say that whatever we start with, we're going to call it A naught. 1,620 years later, the amount that we have is half of that. If we are using this model, then A can be replaced with 1/2 A naught when T is 1,620, right? It's like this ordered pair. T is 1,620, A is half of A naught, and we're just plugging that in. And we're doing that to hope that we can find the K. The good news is when we have this and we divide both sides of this equation by A naught, we get 1/2 is equal to 1,620 K. And we can indeed find K by taking the natural log of both sides of this. That means 1,620 K is equal to the natural log of 1/2. Sometimes teachers will have you just memorize this formula. It will always work out to be that the natural log of 1/2 will equal the half-life time, the t, I don't know, 1/2, whatever, times k, the half-life time. Because this formula will always work out to be this. Whatever this half-life time is always going to be here, and we'll have 1/2 here. That's the definition of half-life, is you grow or you decay to half of what you started with. In this case, k is the natural log of 1/2 over 1620. It asks us to find an exponential decay model for this. Let's go back to this model that we know works. What we need to plug, well, we don't know an A0, so we have to leave that. It's whatever you start with, and then put this k in. Let's go ahead and approximate that, just because it's okay to get an approximation there, as long as we use enough decimal places. See, natural log of 1/2 divided by 1620. That is going to be super tiny, 0.000429. Negative. It's decaying, right? And there's a negative there. Negative 0.000429 t would be a model we could use. We could just plug in however much we're starting with. So, for example, you are a nuclear power plant manager. You are going to know exactly how much of this radium you would have, this radium isotope you would have. You plug that in there, and it would give you an idea of how much you are going to have 10 years later if you plug in 10, 20 years later if you plug in 20, 1,000 years later if you plug in the 1,000 for T. Suppose a nuclear accident occurs and releases 30 grams of this radium-226 into the atmosphere. How long will it take for it to decay to a level of 10 grams? What happens here is sometimes nuclear accidents happen, right? Chernobyl. And we need to know how long is it before it's safe for people to go back to that area. Maybe the threshold for this is 10 grams is a safe level. How long till we can actually go back to that area? That's the kind of question we're talking about here. This 30 grams is the A0. That's how much was released into the atmosphere originally. So we have A equals 30 e to the, I actually really don't want to use the approximation there. I really don't like using it unless we absolutely have to. And I don't think this is any less bad to write than that decimal, natural log of 1/2 over 1620. How long will it take for it to decay to a level of 10 grams? That's asking me, how long is asking me to find T when A is 10. Plug in 10. And I need to find this T, right? I'm going to divide by 30. And take the natural log of both sides. So the natural log of 1/3 will equal the natural log of E to the natural log of 1/2 over 1620 times T. All of that is inside the natural log. We get the natural log of 1/3 on the left side. On the right side, the natural log of E to any power is going to be that power. Natural log of 1/2 over 1620 T. So let me come here. T will equal the natural log of 1/3 divided by the natural log of 1/2 over 1620. When you're dividing by a fraction, it's the same as multiplying by the reciprocal. So I'm going to get this 1620 times the natural log of 1/3 over the natural log of 1/2. And in this case, because I want to know how long, like an approximation is okay here, I'm going to put this in my calculator. Natural log of 1/3 times 1620 divided by the natural log of 1/2. Feel free to go ahead and put these in your calculator so that as you're working along with me here, so that you know that you can do this. I get 2,567.6, and that's years, because that 1620 is in years. I want to make sure that makes sense. That's a big number. That's a long time. If we think about how this works, you start with 30 grams. It is going to take 1,620 to get down to 15. That's the half-life, right? So to get from 30 to 15 takes that 1,620 years. Then to get from 15 to half of that, 7.5, would take another 1,620 years. So we're up over 3,200 years to get down to 7.5. The 10 is between those two, right? Between the 15 and the 7.5. So the time should be between 1,620 years and 3,240 years. This is. So our answer does make sense here. These are some applications of exponential functions. I love how this chapter sort of progresses from here's some information that we need to be able to work through these applications, and then we work through it all, right? And then we finally get to here's how we do it and what we really need it for. So pretty cool. I like it. This wraps up our study of exponential and logarithmic functions in Unit 4.